We present an algorithm that takes any mesh sequence, like this captured face, and decomposes the global deformation into parts that we call sparse, localized deformation components. These components are shown here. Each articulation corresponds to activating a single component. For example, our method automatically finds individual lip and eyebrow movements. It even discovers this vibration of the vocal cord. These components were learned completely automatically. No user interaction, pre-modeled blend shapes, or prior knowledge was used. Our method can be seen as an unsupervised dimensionality reduction technique and is comparable to the popular principal component analysis. However, deformations explained by PCA usually have global impact. In contrast, our method extracts dimensions that are crisp and spatially confined. This can be extremely useful in a variety of mesh processing and editing applications. Here, we show direct manipulation using control points. With PCA components, the eyes are deforming even though the control point is on the cheek. Animators often desire local effects as shown here. Since our components are local by design, they provide this automatically. Our algorithm is initialized by a quick and greedy procedure. We pick the vertex showing highest residual. A support region is built around this vertex based on geodesic distances. We find the deformation component corresponding to this region. This procedure gives us an initial set of spatially localized components. These components are not optimal. We propose a global optimization approach that jointly maximizes sparsity, locality, and reconstruction accuracy. While our method refines all the components globally at each iteration, we show this procedure on a few components for illustration purposes. Every frame can then be reconstructed by a linear combination of the deformation components. This reconstruction also removes capture noise. Our method can optionally discover components in specific regions which are roughly marked by a simple binary mask. This allows artists to introduce semantic meaning into the very process of discovering an underlying basis of deformations. Here we show some examples. Our method works for any mesh dataset, such as this collection of human body scans. The automatically discovered components show deformations localized on specific body parts. The scans don't show the same pose exactly. To our surprise, some of the components found by our method exclusively showed pose changes. We can remove such components, for example, to align the arms in the dataset. Even without performing this pose normalization, we can use our components for specific body part control. Our model also enables statistical exploration and artistic editing of muscle deformations. Since our method provides a local decomposition, it separates visual effects of individual muscles and tendons. How a specific component is activated over time reveals interesting information about muscle activation. This bicep curl is done once without weight and then twice with a heavy barbell in the hand. To counteract this external load, the tricep muscle is summoned. This is reflected in the activation weight of the component. A similar analysis can be done for a component that our method discovered at the tendon of the bicep muscle, which is activated due to pose changes of the arm. We can control the activation of a single component to achieve targeted effects, like this twitching of the deltoid muscle, even if anatomically implausible. We also applied our method for a captured human performance. After normalizing for pose-specific articulation, our method can discover spatially localized groups of cloth folds. We process another captured facial motion sequence. This animation is generated using our learned space of deformations. The shown articulations correspond to activating a single component at a time. Sparse localized deformation components are very suitable for direct manipulation. Here, we show a few example sessions. Thank you for your attention.